Hello, Mass Solar here. This is part 2 of the two-part video series, A Glimpse of Solar. In the first part, we will run over what makes up a heterojunction cell, and in this video, we will talk about the research being done in transparent conductive oxide layers and what the possible effects are by implementing solar technology into society. If you watched the first part, remember when we talked about how TCO has two roles? It acts as an anti-reflective coating, and is meant to act as a lateral transport for the holes moving through the p-doped amorphous silicon to the silver contacts. In other words, conductivity. These two roles are known as the optical and electrical characteristics of a TCO layer. Optimizing these characteristics is the research I am currently doing for a TCO called indium zinc oxide. There are three types mentioned in the previous video: indium tin oxide, indium zinc oxide, and indium oxide. Currently, ITO has been most thoroughly researched, while IZO and IO are relatively new areas. And you might be wondering, why research IZO when we can use ITO? One of the most important things in research is about exploring every path possible. Even if one path has been thoroughly researched through, looking for other paths that might lead to even greater futures is the goal of a researcher. So going back to IZO, it is possible that this material may be favored over ITO, and that is something worth taking note of. The reason for that is because IZO is predicted to have a greater mobility than ITO. This is something very important because it directly deals with its role of laterally transporting holes to the contacts. So now that we know the purpose of a TCO layer from the first video, what describes the material? I've mentioned that TCOs have characteristics. Starting with the electrical characteristics, it deals with how resistive the layer is, otherwise known as the sheet resistance. But wait, what is sheet resistance? Sheet resistance means how much will the hole or electron be impeded over a certain area. Think of it like this. You're the hole standing inside a square pool of water with varying depths. The water is the resistance, and the deeper you go into the pool, the harder it is to move around in any direction because there is more water to move through. You, as a whole, the water is impeding your movement and impedes your movement even more so the deeper you go. But if you move towards shallow water, it is much easier to move around. In the solar cell, you want the TCO layer to not restrict the movement of the hole, meaning you want the pool to be as shallow as possible. So let's look at this equation over here. We can see a few variables that are inversely related to the sheet resistance. E is the elementary charge, which is a constant, 1.6 times 10 to the negative 19 coulombs. Mu is the carrier mobility, N is the carrier concentration, and T is the thickness of the layer. These three variables and the constant define how well the TCO layer transports the holes. Mathematically speaking, increasing any of the three variables would greatly reduce the sheet resistance, but in reality, if we decided to increase the thickness, we can't do that because of the free carrier absorption. Remember that? If we increase the thickness of the layer so much, light will more likely absorb in the TCO layer, and that is something we do not want. This is just one example of the many trade-offs that need to be made when trying to optimize the characteristics of a TCO material. There are too many trade-offs to talk about, so we will not discuss them any further. But as you can see, understanding how restricted we are and varying the three variables is what is meant by optimizing the electrical characteristics. This is the research that is being done. But do not forget, a TCO has optical characteristics, which refers to how transparent the layer is. How transparent it is defined by how absorbing the layer is. How absorbing the layer is determined by how much light is reflected off of it and how much is transmitted through. This is important because we want as much light as possible to transmit through the TCO layer and avoid absorption. If you watched the first part, remember free carrier absorption? Optimizing how much light is transmitted through the TCO layer will minimize free carrier absorption. So how do you quantify transmission, reflection, and absorption? For starters, carrier concentration and carrier mobility determine how much of the light is transmitted and how much is absorbed. If carrier concentration is high, it is more likely for light to be absorbed in the TCO layer because there are more carriers blocking the path of the light. What type of light is absorbed is determined by the carrier mobility. So for example, depending on the carrier mobility, the carriers may be inclined to absorb blue light more than red light. The answer to how this works lies in the units of the mobility, centimeters squared per volt second. You can rearrange the units to be centimeters per second times the inverse of volt per centimeter. This tells you that mobility is the velocity of the carrier in an electric field, which means that the carrier will have a certain frequency, so like an oscillation. If the frequency of the carrier is equal to the frequency of, say, the blue light, then the carrier will absorb the blue light because they are in sync. That then means that the carriers will not absorb red light, and the red light will be transmitted through the TCO, because the frequency of the carrier does not match the frequency of the red light. But then what about reflectance? That is determined by the refractive index of the TCO material. The refractive index can be varied sample to sample to a certain extent by varying the parameters of the tool that deposits the TCO material. In reality, the parameters of the tool are what will determine the carrier concentration and mobility as well. I won't be going into how the experiments are done for ethical reasons, but there are many papers published online that go into detail that you are free to search for. After optimizing the TCO layer, the layer will affect the quantum efficiency, short circuit current density, open circuit voltage, fill factor, and all of those things will determine what the cell efficiency is. The cell efficiency is what determines if a cell is good or bad, and it's those percentage numbers you hear all the time. For example, the commercial cells are only 16% efficient, or the theoretical 25% efficiency researchers are reaching in the laboratory. They are also used to diagnose a cell for any problems. For example, the quantum efficiency can let people know how much free carrier absorption is occurring. Defining and explaining these terms will not be discussed in this video, and maybe in a future video I will go over them. But for now, let's move on to how all of these things are connected and what does it mean for the world. In order to understand the effects of a cause, one must understand where the cause originated from. That is one of the most important aspects of science. Understanding where something comes from is how we have been moving forward as a species. Explaining and showing people how solar energy works is necessary for the public to understand what the effects are in implementing solar technology in our society. So now that you have an understanding of how solar cells work and what new research is being done, you will be able to understand how all of these things will affect our future. As you might know, climate change is a well-known topic right now. CO2 emissions are one of the most contributing factors to the rising global temperature. There are significant efforts being made in order to combat climate change, and one of the ways is by researching renewable and clean sources of energy. Solar energy falls into that category and is one of the most researched methods in order to reduce carbon emissions. Looking a little further into the future, space exploration will be an important path our species will have to take. Space stations, probes, and telescopes will need solar energy to be functional. Increasing the amount of energy available will only allow us to complete more projects and try new experiments we have not been able to do because of energy limitations. But these are things to look at in the near future. What about the future? One of the most appealing traits of solar energy is that it can be accessible almost anywhere in the world because the sun shines its light all over the world. Allowing energy to be more accessible creates more opportunities for innovation to come forth. People who do not have access to electricity will now have one less matter to be concerned about and can focus their energy towards new paths. Instead of people worrying about how they will heat or cool their homes, they can focus that attention towards something else. That something else could be innovative technology that may bring a cure for cancer a step closer, or it may be a new system to purify water so that people can be healthier. It may not always be innovation. It could be that someone can more easily pursue what they want to do in life. But a world where there are more opportunities, a world where people can pursue what they want to do, that is a world where people can truly flourish. A future far away, but a future within reach with the help of solar energy. I want to thank you for watching the second part of the series. I hope you learned something and that you will continue to read and learn about photovoltaics. Thank you.